Hello everyone, welcome to the SAE presentation of conductive layer deposits and the development of an effective bench test for electric vehicle drivetrains. First thing, I'd like to thank the co-authors from Savant, APL, Lubrizol, and Ford Motor Company. My name is Greg Miller. Most of you know who I am. For those of you who don't, I work at the Savant Group. I'm the VP of Engineering and New Business Development. What to expect. So what are we going to talk about today? Well, we'll hit the introduction of the background of the purpose of this test, the starting point, which is the team that we formed in order to accomplish this test, the actual test development, test results, and post-test concepts, and finally, the conclusions. Introduction and background. So what's the purpose of developing a new bench test? Just to have a bench test? Absolutely not. It's normally to be able to solve a problem in the industry. Well, EV's been around for a while, and during that time, a lot of new technologies have been leading the way, both in the lubricant and in the drivetrain. Well, along that way, as shown in the Lubrizol presentation previously, there are several concerning trends that have surfaced. Areas such as deposit formation and corrosion. But on top of that, what is most concerning would be the deposits that actually conduct. So to fully understand the problem here, a test was developed to be able to mimic the actual EV engine and the problems that have been noticed in the industry. Now some work has already been done, and that was kind of the formation of this team. As you can see, some Lubrizol R&D and some APL R&D that had already begun. And so the team formed between Tanis, which is the Savant Group, APL, Lubrizol, and Ford in order to take a closer look at these problems. So what is the actual issue? Well, in the EV drivetrain, we have conductive deposits that are forming from a chemical reaction of the lubricating fluid and the copper at elevated temperatures. Now, this is occurring under low voltage and electrified conditions, both in the fluid and the vapor state. So not all components are lowered down into the fluid at all times. So that vapor state failure is also important. So not only is it conductive deposits, but also deposits and corrosion in general. So we decided that we want to make a test that can take a look at this under the current EV conditions in the actual engine, and possibly even measure the deposit levels and potentially the rate of copper depletion due to the corrosion over time. As you can see, the problem in the actual EV and the breakdown of the copper coils in this particular motor. So as previously mentioned, the formation of the conductive layer deposits is a problem. It is a corrosion product, and it has been identified as a failure mechanism in current electric motors. Different drivetrain formulations may have inherently varying corrosion rates or no corrosion at all, and both the solution being the fluid and also the vapor state. So what do we need to look at? Well, we knew we had to pick a temperature. What was a good selection? Well, we know that the EV drive lines operate in the area anywhere between 130 and all the way up to 180 degrees C. So we did decide on 150 degrees C as a good test temperature, although the temperature of this test can be varied if desired, but 150 was selected. And for the electrical conductivity, it was an obvious selection to pick copper because that's the failing mechanism in particular at this point, especially since the motors have the copper windings. So a circuit board was selected with traces to put on it that are not coated, and it was only for consistency purposes that the circuit board was selected. So this is not a circuit board test per se. but a circuit board is utilized for consistency purposes for putting traces of copper on the board. Let's talk for a moment about the test boards. Here's a test board showing the actual connections, the outer voltage loop for this set of connections, the lower traces for the set of connections, and the upper set of traces. Notice the traces are very close together for both the upper and the lower, but the voltage loop is just one large loop going all the way around where the signal is applied. The board is then placed into the test cell. And of course, there's two boards and a spacer, which you'll see in just a moment. The test cell then is filled halfway with a fluid. And that fluid line sits right about there throughout the duration of the test. The boards are teamed up in tandem, along with a blank board in between, which you can't see in the drawing here, and placed into the slotted carrier. This carrier puts the proper distance between the two boards. The oil is filled halfway, which is inside of the test cell carrier here. So this is the actual test cell. So this entire assembly is lowered down into here. Oil is filled approximately 15 milliliters to be halfway on the particular board that is shown. This set of traces is in the oil. This set of traces is in the actual vapor. So then we can monitor both in the oil and the vapor with these particular copper traces. Where does it go from there? Well, the test cell is then lowered into a carousel, which is just a holder. That carousel is then in turn loaded into the bath at 150 degrees C. What are the test parameters? Let's look. Other 10 test cells are loaded into carousel, which was just shown. This bath type was selected for this work in order to maintain solid temperature control. Circulation of the bath allows us to control temperature more efficiently. Covers are placed onto the test cells. A 5-volt DC signal is supplied to the voltage loops, which were shown earlier, in order to track the resistance between actual test runs. Shorting due to deposits or an open is shown during the test due to failure, and that is tracked during the time of the test. The test time is 1,000 hours in duration. However, we are trying to reduce that test time. So for the test results that we'll be talking about today, there were 4 series of tests that will be shown here. Series 1, 2, 3, and 400. The samples that were run that are identified here were actually 2 field samples, one a failing field sample, that is a known sample from the industry to fail, and one that is passing. Then there were several others that were off the shelf, suspected failing. These were purchased off the shelf, and then one that was suspected passing. Information that we did get from various oil companies and OEMs. Most of the analysis are done with samples 1, 2, and 3, although there are some results shown for samples 4, 5, and 6. Test Series 100. All test parameters were done without covers in this first Test Series 100. It was the beginning of the testing just to show that we could have some failing results with these particular samples 1 and 2, the known field failing and the off-the-shelf suspected failing. Here are the results of sample 1 and 2. Sample 1 failed right between 750 and 900 hours. And this is in the oil. This is the amount of resistance, which is a lot of resistance at the beginning. And as the test ran, you can see that it gets lower in resistance due to deposits and operation temperature, of course, has an effect of that. And then here's the time in hours. Sample 2 failed between 200 and 450 hours. In the vapor phase, this is in the upper portion of the board, sample 1 still failed between 500 and 950 hours. Sample 2 failed between 100 and 300 hours. You can see the breakdown, very evident with both samples. Again, both in the oil and in the vapor. In conclusion, for Series 100, both fluids showed consistent failure in the oil and vapor. The test was repeated in various test cells within the bath multiple times. Test Series 200. In this test, the samples were actually covered. So some were covered, some remained open, so that we did both in order to see the differences between the type of cover that we put on. However, we also added a known good oil. So sample 3 was a known passing fluid, so that was added. And so the other ones were repeat tests, both covered and uncovered, as mentioned in the previous slide. Test results. This result is showing the sample, how it performed in the oil. So they're divided between covered and uncovered as shown here. So this is sample 1 in all of these results. We have sample 1 covered, sample 1B covered, and then sample 1 uncovered, and sample 1 uncovered. So these are the 4 tests. And like previously, we had results very similar to what we had before in the uncovered. So that's these 2 colors here. And then the covered, we did shorten the test. The test actually shortened a little bit. So we saw that it's probably important. We saw more variation too. So covering these samples is already proving to be important in the oil. And then the vapor phase, this is blown up. Note that the axis here starts at 400 hours. So here is the failure for the covered here. We did have one uncovered one that did fail a little bit earlier, but definitely the 2 covered samples started showing failure here, even though it did straighten out a bit here. There is notification here of failure early on. So both in the oil finger pattern and the vapor finger pattern. What about the passing oil? Sample 3 was a known good oil from the field. But here's what we see when a sample is truly a good performing fluid. In the oil, as temperature increased and it stabilized, it flattened right out for the resistance, and there was no shown failure. And in the vapor, similarly, we saw the same thing. A little bit of noise in here, but overall looks very, very good. So both covered and uncovered showed really no difference for the good oil. So for us, that was excellent news. knowing that we could shorten the test for a failing, but the passing would pass. Now, what about the continuity loop? It's one thing we haven't talked about much, is the outer continuity loop. Well, for the failing fluid, these are the types of graphs that we've noticed for the failing fluid in the continuity loop. And there is some information to be gleaned by that because the passing fluid is very flat. So that continuity loop is all by itself, and so we can see the degradation of the copper over time. Test series 300. In this test, we added more sample types. So we added sample 6, which was a suspected passing sample. Added sample 4, which is a suspected field failing. Sample 7, the same, and we repeated sample 1, which was a field failing fluid. And here are the results. So sample 4, in the oil, we saw the breakdown and an ultimate failure. And in the vapor, the same. We did have a slight aberration early on in the process of this particular sample. Could be related to temperature of the bath. Sample 5, similar results. And in the vapor, the same. We did have one of in the oil show that it was stable. Saw a decrease, it was a continuous decrease, but we didn't see the aberrations of the shift in resistance here. But we did see the failure in the vapor. Now in this one, we did run the passing fluid, sample 3, which is shown here in the brown. And it passed again, both in the oil and the vapor. And then sample 6, shown here, was a suspected passing fluid, but did not actually pass in the oil nor the vapor, except for here. We did see that that did not fail. So here's a synopsis of test series 300. 2 new samples were added, were repeatable in the port and the oil. In the vapor phase, one test on sample 6 did not reproduce. It was observed that some areas of the bath were producing higher temperatures than others. That could explain some of the differences we saw in the data. So at this point, we did realize that controlling the bath temperature within 1 degree is a big advantage for repeatability and reproducibility. Test series 400. In an effort to shorten the test, 1,000 hours is a very long test. Since we already had pretty good repeatability, we thought we could even improve our repeatability and reduce the test time in one stroke. And that would be to bring those traces on the board a little closer together. So we did that. And just as a note, early in this process, we did notice in order to stabilize our voltage, there was another setup that we could do. And this was added in these test phases to improve the reproducibility and repeatability. So here's the results for sample 1. It is easily viewed that the sample 1 standard spacing in the previous boards repeated with the exception of some noise that we had here, which was electronic noise, which we were able to improve in future tests. But here it started breaking down right around the normal 600, 650. We were able to stop the test at about here where it was breaking down. But the spacing with a tighter space, so in these colors here for both the yellow, blue, and green, started breaking down a little bit earlier in the oil. So that was very good news. We were able to shorten the test with these tighter spaces. When looking at the vapor state of the same board, we see a similar result where in this standard board spacing, we see it starting to break down right about in the normal spot we saw before. However, a little bit earlier, when the vapor state with the board where the traces were closer together. So this is a really good indication that the test should be able to be shortened up from the 1,000 hour test, and that is very good news. The results of sample 3, which is our good sample, you can see here that we had good results in the oil and good results in the vapor. So no matter if they were tight or not from previous runs, all these were run as tight because we had a lot of data already on this particular fluid with the standard. Let's look at the statistics on the results. So in a 1,000 hour test, fluids that failed the liquid 100% of the time always failed. Fluids that failed in the liquid and vapor both repeated 87% of the time. Fail vapor only, we don't have enough for statistics for vapor only. And then passes with no failures, 92%. That's relatively robust. And we recommend in the future for 3 replicate samples and potentially a minimum of 2 in the future. Test results appear to be a good discriminator both in passing and in liquid phase. And then when they're failing both in the liquid and the vapor, we have good repeatability. Some post-testing that was done shows that we could potentially look at the end of test in comparison to the fresh sample, both with boron, which is found in detergents and anti-wear, and maybe plating onto the copper substrate, and we see a significantly larger amount of solubilized copper in one of the samples. Phosphorus and calcium did not show any significant changes. And here's some interesting facts with boron. This is the sample fresh, and then reduced boron content in the used sample at the end of the test. Very interesting. What about copper? Neither sample showed copper in the fresh sample, but afterward, we had this much solubilized copper here and even more in sample 2. But this is very interesting when we did the filtering process. The boards were disassembled and rinsed, and once rinsed, the material was collected and filtered through a pre-weighed filter and allowed to dry at 100 degrees C. Here's an example of a failing board where we got deposits, and a passing board, of course, would not have deposits. For the sample that showed a lower amount of soluble copper, had more copper in the filter, and vice versa, sample 2, which had a lot of soluble copper in the oil, used oil, showed less in the filtered material. So conclusions of the post-test series. A recommendation is being moving forward to look at ICP analysis of both the copper and the boron and the fresh and end of tests is very valuable. And the filtering process appears to track with the ICP analysis. It could be an interesting tool for the methodology being developed. Overall conclusion, a conductive test is shown to be crucial for the industry. Having a commercially available conductive test will eliminate variability from test to test. The test described today shows consistent results using copper traces on a circuit board that are repeatable and available. Having a shorter test with tighter traces provides the industry the good opportunity to improve the test. Temperature control of spacing of the board within one another has proven to be necessary and important. The samples run in this experiment, both field failing and off the shelf, are repeatable and mimic real electrified driveline data. Determination of end of time failure times is yet to be determined, but will be with the help of OEM input. And the continuity loop data show possible opportunities for more information to be gleaned. Thank you for your time, and I look forward to all the wonderful questions. Have a fantastic day.